I'm having this other third session, even though some of you are not currently connected, but I hope you'll be joining me because you receive a notification. Otherwise, you'll be watching the recorded session. So the purpose of starting this session, or the aim or the goal of this particular session is, stem from the problem that we tackled yesterday. I'm going to share the screen with you. If you recall, yesterday we solved a problem where we showed that a certain function f from omega to r defined by f of n equal to -1 to the n. If you recall that example, the purpose was to show that that function is measurable, or f measurable. F was one of the sigma algebra that was defined over the set omega equal to 1, 2, 3, 4. So as you can see on the slide, it was this function, omega being 1, 2, 3, 4. So in order to prove that this was, a measurable function, a f measurable function, we endow R with what I call the Borel sigma algebra. And we saw from the previous lecture that the Borel sigma algebra was was a sigma algebra generated by open sets. That is, you have a topology, and all the open sets of that topology will generate a topology. Will generate a sigma algebra, which we denote by BR, the Borel sigma algebra. So, in the definition of the Borel sigma algebra, we mention topology by open sets. Okay, so before proceeding to what is the Borel sigma algebra and what are the elements of the Borel sigma algebra, we are motivated to define what is a topology, a general topology defined by open sets. So that's the main motivation of today's class. We are going to define along the way with our sigma algebra or measure theory. We are going to define at the same time what is a topology, which in fact is supposed to be tackled in this class, in this module. So we take that opportunity to tackle that particular section or part of our program. So as you can see on the slide, we assume that we have X, an arbitrary non-empty set. This is our underlying set, and we are going to define the topology on X. So as usual, we take our calligraphy X to be a subset of the power set of X. So this is a collection of subset of X. It's a family or a collection. So such a collection, remember that when we define a sigma algebra, it was through a collection or a subset of the power set of X. So the way we define a sigma algebra is the same, or is a similar way we define a topology. So a family of subsets of X is called a topology in X through open sets if the following three axioms are satisfied. So you can see that this first axiom is similar. Okay, I will not say similar. please let me make a point here and make it clear. In the definition of a sigma algebra, recall that in the definition of a sigma algebra, from the prescribed textbook, we had two conditions, two axioms. Sorry for the inconvenience. I'm having problem with the Acrobat Reader software. Okay. So for the sigma algebra, from the prescribed textbook, we had two axioms, 1 and 2. So the first axiom was for any element. Okay, let's say that our sigma algebra is what? Okay, let's use calligraphic A, right? So for any A in the power set of X, A is a sigma algebra if for any A in A, that is, this is a subset of X, the complement is also in A, and for any A1, A2, that is a countable union, right? Of course, all these elements have to be in A, right? The countable union of all these A also have to be in A. So these are the two axioms. So these are the two axioms that were given in the prescribed textbook, but I said, and that is also the definition that is used in most of the textbook. To add to this one, another condition here, that either the empty set or X itself is an element of the sigma algebra. I will call this, maybe let's put prime here, since this is okay, no problem. So we don't need to put both, right? One is enough. If we can show that the empty set is there, this second condition will imply that the complement of the empty set, which is X itself, will be there. So we don't need to impose the two. That is, we don't need to impose that both the empty set and the underlying set X are there. If you assume it's still fine, but it's not necessary. Okay. So what I want to say with respect to this is that this first condition, these two conditions, in fact, we can use these two conditions to show that the empty set and X are element of A, but it's a long process. That is why in the definition, many authors include the condition that the empty set is also in the sigma algebra as an axiom. I repeat, these two conditions, without the imposition of the fact that the empty set has to be in the sigma algebra, are enough, because from condition 1 and 2, we can prove that the empty set is an element of the sigma algebra. But this will be another long process, because to prove that is in fact a proposition. It is a technical process. So we don't need all that. We can just impose this and this first condition that says if an element is in the sigma algebra, its complement is also. From that, we also have the consequence that X also is in the sigma algebra. I'm making this precision so that things will be clear and there will be no confusion. And also due to the fact that for the topology, these are imposed already. They are imposed. That's the first requirement. Both the underlying set X and the empty set have to be in the sigma algebra, but in the topology. But for the sigma algebra, you only need the empty set to be an element, and these two requirements also. So we have three requirements here: empty set being an element. For any element, the complement is also an element of the sigma algebra, and the countable union of element of the sigma algebra is also an element of the sigma algebra. So that is for the sigma algebra. So remember, we need these three conditions, even though these two are enough. But for that, you have to prove this, which we don't need to, right? Okay, so that was a remark that was worth mentioning, and I hope this will be clear. Good. So these are the three axioms. We need both the empty set and the underlying set X to be an element of the family. The family being calligraphic X. Okay, and the next condition is that an arbitrary union of element of the topology has to be an element of the topology. This looks like the second condition or the third condition for the sigma algebra, but for the sigma algebra, remember that we need a countable union, but here it's an arbitrary union. It might be countable or not countable. It's an arbitrary union. So you have the arbitrary union and finite intersection for the third condition. So for you to remember, the last condition of the sigma algebra is similar to this one, but the difference is that you don't need countable union. It's an arbitrary, meaning that it is even more general. So you keep that condition for a topology, and you add a third condition, which is a finite intersection of element of the topology is an element of the topology. So this is called, the second condition here, or the second axiom is called closure by arbitrary union, and the third axiom is called closure by finite intersection. So you can see that the definition of a topology is a bit similar to that of sigma algebra. But in the definition of the sigma algebra, you don't have the third condition. And the difference is that in the definition of topology, you don't have the closure by complement. That is, for any element in the topology, you don't require the complement to be an element of the topology. So those are the distinction between the two. Good. Now, this being said, we know, or from now on, we know what is a topology. You see that you don't need to have a closed interval, open interval, as it is the case in R. You don't need that, right? Even though, for the case of R, with the metric or the distance being the absolute value, an open set for that topology is an open interval. So it will depend on the case-to-case basis. Okay. Now, what do we call an open set? It's just any element of our topology is called an open set. That's all. So if I have a family X that satisfies these three requirements or these three axioms, any element of that family is called an open set. Now, the complement we call a closed set, which we don't require. In fact, we don't require that complement to be in the topology. We don't. That complement is in X, but not necessarily in the family. You can see, this is the topology. We say that all these elements are called what? Open set. So you understand, it's clear that a closed set might not be, or might not be in the family. It might not be in this family. Okay, now let us look at some examples. So we are given X to be the final sets made of these 4 elements: alpha, beta, gamma, rho. And we have 3 family of subset of X. In fact, they are defined by extension, as you can see on the slide. The first one, X1, is a topology in X through open set. The second one also is a topology in X through open set. But the last one, X3, is not a topology through open set. Okay, but before I proceed, look, if we take alpha, we know that alpha is an open set. Why? Because it's an element of X1, and X1 is a topology. So open set will be X, the empty set. So they are both in the topology. You can see that alpha is an open set. Alpha beta is also an open set. Alpha beta rho is also an open set. Now, if you take the singleton alpha, we know that it's an open set, and by definition, its complement will be a closed set for this topology, because when we say open closed, it's for a particular topology. Because alpha being an open set, if you take alpha to R, first of all, alpha is not necessarily an element of R. It can be anything. But now, we know all that in R, a singleton cannot be an open set, but in this case, it's an open set. Now, if you take the complement of this, of alpha, it will be what? It will be the set made of beta, gamma, and rho. And that will be a closed set for this topology, because it's the complement of an open set. Now, you have 2 elements of X1, that is X and the open set, which are both open and closed sets. Why? Because the complement of the empty set, which is, the empty set is an open set, and its complement will be what? Will be X. But we know that X is an open set because it's an element of X1. But because it's also the complement of an open set, the empty set, X is both open and closed, right? It's an open and a closed set at the same time. And similarly, the empty set, which is the complement of X, is a closed set. Because X is an open set, its complement is a closed set, and its complement is the empty set. So the empty set also will be both the closed and open set for the topology. So this is very important to understand. Now, for X3, why is X3 not a topology? If you recall from the definition of a topology, we saw that an arbitrary union should be, or a finite intersection of element of the topology should also be in the topology. Now, let's look carefully. If we take this union, I mean, if you take a finite intersection, it's easy to take a finite intersection. Remember that from this one, we say that if you have a finite number of elements of the topology of the family, its finite intersection has to be in the topology. Now, if you take these two in X3, if you take these two sets, alpha, beta, beta, gamma, rho, if you take the intersection, because it's a finite intersection, if you take the intersection of these two, it gives us the singleton beta. It has to be in the topology, but if you take the intersection, the singleton beta is not there. You see? So because the singleton beta is not there, we stop and conclude directly that this property is not satisfied. The third axiom is not satisfied. Therefore, this cannot be a topology. So it is clear to see that. Okay, that's even. All right, so we can stop here. You already know what is a topology, and you have two examples of topologies here defined on X, and you have a case of a family of subset of X, which is not a topology. Now, let us go back to the Borel sigma algebra. Now that we know what is a topology, we can go back and study the Borel sigma algebra of R. That is BR, calligraphic BR. Good. We are going to study okay, now you recall from the definition, this definition, this one. Let me frame it, box it. Oh, sorry. So you see that for us to prove yesterday when we proved that F is F measurable, we had to select an arbitrary element of the Borel sigma algebra. And that will be the case because we'll be dealing with real value function. We need to know the topology or the structure of the element of the sigma algebra BR, the Borel sigma algebra or Borel set. We need to know their structure in such a way that if we want to prove that something is measurable, we'll be able to write a generic form, like I did yesterday. You can see I just use A equal to the open interval from negative infinity to A, where A is an element of R. And I use that as a basis or a representative of the Borel sigma algebra, because if I use that element, from that element, it would generate, or it's a representative of the Borel sigma algebra on R. And it's not the only one. There are many forms of A as a representative, because when we say for any, we are not going to select all possible elements because there are infinitely many. So we cannot start selecting each one. We take a representative, or we take A having a particular form that will represent the entire sigma algebra. So that's what I did yesterday. So in order to do that, we need to know the structure of the element of the Borel sigma algebra. Otherwise, you'll not be able to prove that a real value function is measurable, because you need to know the generic representation of an element of BR. So that's why it is important for us to try to see the structure of BR. So this being said, you are now motivated to learn or to know the structure of BR, and that's what we are going to do. Okay, so what are, okay, so here I will write, okay. Of BR being the Borel sigma algebra on R. And in order to know the structure of the Borel sigma algebra on R, of course, R, we know we can write R. R, in fact, is this. R is an interval. It's a set, but it's an interval. This is R. It's an open interval from negative infinity to positive infinity, or just infinity. So if you don't append the sign, we know it's positive infinity. So that is it. That is how we write R. Now the next thing that we are going to do is to define what we understand by this BR. If you recall, it was said in a general setting, a Borel sigma algebra is for topological space, right? So assume X tau is a topological space. Topological space. Meaning that this tau is a topology on X or in X, the topology in X by open set. Right? Okay. Now, the Borel sigma algebra on X is denoted by Bx. And this is equal to what? The sigma algebra generated by the topology tau. So this is the definition. So on R, we have our open set, which are open intervals. And we take the topology generated by open intervals in R, that gives us BR. Okay. Now, yesterday I took this form, open on both negative infinity and A. I could have also closed here. Or you can even use the open interval AB. So all possible intervals will also generate the same sigma algebra. And this is important to know. So I'm going to show that. So let us, I will first define it here. So I already said that for BR, we just replace X here with, we can take X equal to R and tau, the topology on R, that is it, and then it will generate that, right? Okay, now, I'm going to use it's like a definition, but I will not call it definition. The small sigma algebra, the smallest sigma algebra over R containing all intervals of the form negative infinity, like this, comma A. I can open or close, but let us in this kind of definition use close. With A, an element of R, is called the Borel sigma algebra. The Borel sigma algebra. And we denote it by You can denote it by B, like this, but this might be confusing, because you have to indicate BR, like that. Then we know it's the Borel-Sigma algebra on R. Because you also have the Borel-Sigma algebra on Rn, or on any other set, provided you have a topological space there. Now, any element of BR is called a Borel set of R. Any element of BR is called a Borel set. A Borel set of R. So these are definitions. We have here Borel. We have here the definition of Borel-Sigma algebra. We have the definition of Borel set of R. Okay. We say it's a sigma algebra because we wrote it here. It's a sigma algebra. But because it's a sigma algebra, we know already by definition of a sigma algebra that the complement, an element that is in a sigma algebra, its complement will also be, because now we are going to talk about the structure. Yeah? Remember, we say structure of the R. Structure. Which are the elements in BR? That's what we are trying to see. Even though BR is generated by open set of R, remember open set are open interval, but even elements that are not open interval are also in R. Don't forget it. Meaning that if I have an open interval, which is an element of BR, remember that its complement, which is a closed set for the topology, will be an element of the sigma algebra. So in the Borel sets are not only open set, they are open set, closed set that are open in one end, closed on the other end, and so forth. So any type of interval that you can imagine, and even singleton. Yes, even singleton. Why? Because the singleton is what? It's a closed interval containing that simple element. So any element of R, any subset of R that you can imagine, are in the Borel sigma algebra. That's really interesting. That's why I call this structure of BR. Right. Okay, so let us write that. Since, okay, now this is about the structure. Since BR is a sigma algebra, if we have, or we select A, B, two element of R, and we assume that A is less than B, of course, Then the following are Borel sets of R. Now we are given the structure. The following are Borel sets. So first we start with the first one, 1. Now you see that here we have this type of open interval, a, comma, infinity, like this. You see, so meaning that even here I could have taken this a infinity for our a. I could have taken that to be the representative of BR and use it to prove that for any a, the open interval at a to infinity for any a, right? Because when you say for any a, you will cover R. You will cover R, right? So I could have also used this instead of the other one. So you can see this one. So now, why is this? Why is this a Borel set? Can we write this as the complement of something? Yes, this is the complement of negative infinity a, close here. So if I take the complement of this, it gives us that. Because what is this? Remember, the underlying set is R, so it's R minus this. So this, by definition, is R minus this interval, negative infinity to A. So we can say that this is an element of BR, because it's the complement of an element of BR. Right? Because here in our definition, we say that this is the smallest sigma algebra containing all interval of this form. So meaning that this is the interval of this form generate this sigma algebra. If I call this K, remember last time let me write it here. Remember when we defined this one, a sigma algebra generated by a set. Now here, if I take K to be this, the collection of all this, that is K, I take K to be the set of element of the form negative infinity to A, close there, A in R. So you can see that our BR is nothing else than the sigma algebra generated by this set K. So this is what we use here in our definition. Even though you can also take K to be the open interval AB, where A is less, A and B are two elements of R, and A less than B. It will give you the same thing. It will generate the same topology. I mean, the same Borel sigma algebra. But in our case, this is what we selected. As I told you, we could have selected the open interval from negative infinity to A, open at A, not close as we did here. So it doesn't matter what you choose. Okay, So now you can see that this gives us the same topology because we take the complement, we have this, so we can also use this to generate our Borel set, sigma algebra. Okay, so this is a Borel set, so we proceed with the list. The second one, we can take the interval here, open at A, comma, close at B. It is similar to this one, where we replace A with B, and we replace this with A, even though this one is not, a negative infinity is not an element of R, right? It's an element of R bar. That is it is an element of the closure of R. Okay, I think it's better to write it, to say this that way. But how can we write this? How can we write this? We can write this as the intersection of two elements of the sigma algebra. We know already that this negative infinity to a certain B, because remember, this has to be an element of R, but we already said that B is R, so we can replace this. So this is exactly of this form. Open at negative infinity, close at an element of R. So it can be A, it can be anything here, provided it's an element of R. So that's what we have here. So it's similar. So we know already that this is an element of the Borel sigma algebra. So we take that intersection with another element of the sigma algebra, that is this one. Because we have just shown that, I mean, from one we show that this interval is in R. So we in the Borel sigma algebra. So if we take two elements that we know already that are in the sigma algebra, whatever if we take their intersection, whatever form we obtain is an element of the sigma algebra. So intersection with the open interval, open at A to infinity, right? So this is an element of BR, and this is an element of BR, and this is an element of BR from the first, I mean, from the first result, 1. So A is less than B. So for this one, let me draw something here. This is our we have this. So this is negative infinity here, and this is infinity. We have two elements here, A and B, two distinct elements, because we say that A is less than B, so we have this. The sign doesn't matter, just need two elements. Now, from negative infinity to B, I will shade it in red. So this is negative infinity up to B. And this is close at B. So that's the first. Now the second one, I take the green color for the second one from A, open at A to infinity. So here at A, I open at A to infinity. Now, if I want to look at the intersection of both elements that are in this first interval and in the second interval. So you agree with me that it will be the part that is shaded by the red and by the green color. So you can see that it will be open at A here. Obviously, when I write like this, it means that it's open, right? So meaning that it is open like this at A, even though open means like this. Or I should have even written it that way to avoid kind of confusion. Okay, so this is open. Okay, just understand that this is open at A, open. Now, if you write this shaded bar, doubly shaded, will give us an interval that is open at A up to B. But B is closed. It's closed at B. And that's exactly what we have here. Open at A, close at B. So we are done with that. So that is the second now the third one, the third family of interval is the interval negative infinity, comma, A. Now, it was closed, we can open it also. And this is the interval that I used yesterday in our proof. It was open at negative infinity and at A. That's the interval we use. And you take that for an arbitrary element of R. So you can vary this in R and prove whatever you want to prove. Okay, so this one, why is it there? We need to show that it can be written as either complement, intersection, or arbitrary union. Finite intersection or arbitrary union. You can say that this is a finite intersection. But we can write this as an arbitrary union. How can we do that? This indeed is equal to the arbitrary union. When you say arbitrary union, arbitrary, any type of union, provided you have your result. Not necessarily countable, right? Not necessarily countable, but it can also be countable. Okay, so if we take this interval, negative infinity, to be sure that it remains negative infinity, in our union, we keep this part negative infinity. And here, we will put something in such a way that when we take all the union, right, it has to be one of this form because these are the elements that we know already that they are in the Borel sigma algebra. So here, we can use something of this form because we know that this is there. I cannot use that because I already have negative infinity here. So for negative infinity, I can select something of this form. Right. In such a way that when I will take the whole union, it will exclude that, it will be open because now we'll be using closed, but it will be open when we take an infinite union. So we have here A, I can take A minus 1 by n and close here. Because we know that the limit of this will go to 0, right? When n goes to infinity, in the limit, right? And we know that the limit will not be, because this will be the limit. So we could open the interval, and therefore it will give us this. So we take that union. Okay, this is n, so we take the union for n, because this cannot be 0, so we start from 1. Countable union to infinity. Okay, so that is it. And you can prove this. You can prove that. In fact, this is an exercise that I'm giving to you. To prove that two sets are equal, what do? If I take an element here, I prove that it's there. Therefore, this will continue in that. And conversely, if I take an element here, I will show that it is there. right? So I showed a double inclusion. A contained in B and B contained in is equivalent to A is equal to B. So I'm asking you to prove this equality. No? Prove that this set to the left is equal to the set to the right. Prove the equality. Homework. Okay. So you see that this for each n, this is in the Borel sigma algebra. Why? Because an element of the sigma algebra, we saw that an element of this form is in the sigma algebra. For a fixed n, A minus 1 by n is an element of R. Therefore, this is an element of R. Now, if you take a countable union, which is part of arbitrary union of element of the sigma algebra, is still an element of the sigma algebra. Therefore, this is an element of the sigma algebra. Okay, so I will quickly write the other ones. I will not, otherwise, if I have to explain each time, the time is against us. I want to stop in the next. What? Let me check how long we have already spent. Oh, almost 57 minutes since I opened the Microsoft Teams. Maybe I didn't record directly at that time, but yeah, almost 57 minutes. So I want us by the next 5 minutes we should stop. I didn't want this to be very long, but that's fine. So the fourth family of element. Now we can use this structure already. We know that this is an element, right? I can take this complement. So if I take this complement, we have something on the form A, comma, infinity, like this. Remember that here we had A, open at A to infinity. Now we can show also that close at A is also there. But this one is what? It's just a complement. It is the complement of negative infinity to A complement. Negative infinity to A complement. That is this one that we just take the complement. And what is that complement? It's R minus that. R minus this. You can just draw this. You can just take this, draw it here from negative infinity to A. Now you open at A. If you open at A, it means that A is not there. A will be on the other side. So it will be close at A to infinity. That's exactly what we have here. All right, now the fit structure, we can write the interval, the open interval AB. The open interval AB, you just take the intersection, negative infinity to B, like this, with A to infinity. We know that an interval of this form, that's from 3, is an element of the sigma algebra. And from the first one, this is also in the sigma algebra, and the intersection, which is the open interval at A and B. Okay, now the sixth one, we now have the closed interval AB. And the closed interval AB is just the complement of the union of these two, right? Arbitrary union, if you take the union of these two, is an element, and if you take its complement, it's still an element. Something of this form. That is, when I say these two, I mean I can take from negative infinity to A, and then from B to infinity. It's the same, of the same form. So the union will be there, and then the complement will also be there. So if I take R minus this union, negative infinity to A, union of B to infinity. Which in fact the complement of this union. So this is given by that. Just draw the number line, put this, and just highlight the complement of the union. So you identify the union, takes the complement, you see that gives you the closed interval. So closed interval is also there. And 7, for any element of R, the singleton made of that element, so it comes from this one. If I take A equal to B, the interval, the closed interval AA, which is made of A only, is also an element of the sigma algebra. Right. 8, the set of natural integer due to this, right? Due to this one, we saw that because if any element of R, a singleton made of any element of R is in the sigma algebra, you agree with me that if you take A to be a natural integer, and then you take the union of all natural integer, because we saw that an arbitrary union will still be there, then therefore we can say that N will also be in the sigma algebra. Why? Because it will be the union of singleton N, where N is in N. So that N in N, we know that we can take from 1 to infinity. I can even add 0 here, right? You can take this from 0 to infinity. Okay. Or if you want to start from 1 to infinity, then you remove this 0. So N0 or N, they are both there. And similarly, with this one, you agree with me that even Z, the set of integers, right, is also there. Okay, so the other one, 9, Q, the set of natural, the rational numbers. This is the union where N are integers. Of course, N has to be non-zero because you cannot divide by 0. So these also are there. Why? Because this is an element of R, don't forget. If this is in the, I take the union. So we know that this is a real number. If I take a countable union on both M and N, it's still in the sigma algebra. So all these. Now, if I take the complement of this, because this is there, so I can take its complement, which is a set of irrational numbers. So if I take the complement, which is R minus Q, is also there. obviously, we're able to prove that any form of subintervals, you can see, this is a subinterval, interval. Any form of interval in R, you can see that all these are the possible interval. Close interval, open, close, semi-open, close interval, whatever. Because remember that this is an interval, right? And then their union gives us also this. So we're able to prove that any form of interval in R is an element of the Borel-Sigma algebra, BR. Now the question that one may ask is any form of subset of R in the sigma algebra? No. Are all subsets of R subsets question answer no. And we will stop here for today. Thank you for your kind attention. I hope you have enjoyed or you will enjoy this presentation. God bless you and see you next time. This is our class that we are supposed to have later during the course of later in the night. So this is the session. And tomorrow I will record another one because remember, last week we missed our 2 sessions, so we can catch up. But since it's just recorded video that you can watch at any time, I hope you agree with me that I can record as many videos as possible so that you gain more knowledge. Okay, thank you. God bless you and see you next time. Bye-bye.